So let's take a look at how we measure algorithms, because I hinted at this in the previous video, but it's important to understand we need to consider algorithms at three levels typically. It's best case, it's worst case, and then the normal operations of what's happening in between. So the idea of the best case is everything's perfect, everything's optimal, the data's the way we want it to be, coming in, it's been prepped in a beautiful way. In an empirical sense, everything's running perfectly. The algorithm's written correctly. No bugs. There's no interruptions from the processor. That's ideal. Realistically, the best case is only going to be achieved in very rare circumstances. It's not going to be achieved all the time. And if it was, we would never have to run that algorithm. If the data was already sorted, why am I sorting it again? But what we can do, and what we'll see in the next video, is there's cases where if we can tweak the circumstances to make the best case more probable, we can actually take that best case, get closer to that best case performance most of the time. Um, so the worst case performance is clearly the everything's gone wrong. No matter what happens, though, it's not going to do any worse than that. So as we talked about before, if I'm searching a list and doing a linked list, there's 1,000 items on the list. The worst case scenario is I look at every single one of the items, all 1,000 of them. But the normal case is going to be something less than that. Probably, if you did it 1,000 times, the average is going to be closer to 500. Again, the way statistics works is that might not be 500, might be 400, might be 600. Just depends on your luck over those 1,000 tests. But it's going to push the more the law of large numbers is the more you do, the closer it's going to be to that true medium. So the important thing about the normal case, though, is we do have to understand what the standard data looks like. What does randomization really mean? Data is not truly always random. When people put in values, by typing them by hand, they may tend to be less than perfectly normally distributed. If we say we're going to sort things alphabetically by the first letter, well, the people have the letter Z, X, and Q much less often as a last name than they do, B, D, and T or something like that. So the data is not necessarily equally distributed. There might be tweaks in the data where we have to, decide we're going to represent it slightly differently, or there might be ways that it favors certain types of algorithms over others, the way it comes in. And so there always are circumstantial things to consider. We can't just simply say, for all cases, this is going to be the best. So that's where the idea of empirical evidence weighed against analysis is useful. So here is not even some great sampling. I basically what I did was I ran each of these algorithms 5 times and averaged it over over all of the algorithms, and then I stopped some of these ahead of time. So we can see, starting with a count of I think around 5 or 10, all of them perform essentially instantly. 0, 1, 2 milliseconds. But by the time we reach a size of 5,000, we're starting to see that the bubble sort's pretty crappy. It's actually an exponential growth right there. I'm sorry, a quadratic growth right there. It's x squared. And the insert and select sort are starting to look pretty bad compared to the rest of them. By the time we hit 10,000, the bubble's really bad. Insert and sort selection not so good, and at 20,000 I gave up on it because it was taking longer to run those cycles than all the rest of them combined by far. So it's not until about 50,000 data items that we start to see a differentiation between the other ones. At that point, the merge sort ends up being a little bit slower, at least my implementation of it. And then by the time we hit 500,000, it's clear that the merge sort is inferior to the rest, but the other ones are somewhat similar. Um, and then when we do the last jump right there, we can see that at 1,000,000, which is here, let me just throw this up now. Note this is a logarithmic axis here on the x-axis, which you can do logarithmically either way. It is deceptive. That's why you have to always look at axes right now. But these are not all growing, quadratically over time. They look quadratic because of the shifting to the axis. I just want to make sure I point that out. But by this point, we can see the merge sort's definitely slower than everybody else. The heap and the quick sort seem to be slower than the shell sort, but that's because I'm adding a shuffle to my my quick sort. If I take the shuffle out, the quick sort and the shell sort start looking quite similar, and the quick sort might be a little bit quicker. So we're going to actually look at a couple of these here in analysis later on, but I want you to see this is the empirical data that backs up the analysis that we're going to go look at. Um, the analysis that we talked about is sometimes called an asymptotic analysis, where what we're saying is we're looking at the worst case scenario. We're taking away all of the other details. We're going to look at the data in a specific scenario, and so this analysis sometimes is referred to as the big O notation, the big O analysis. The O being a symbol that we're going to see in a second, but it's the worst case scenario that's focused really on the scale of the algorithm, not the exact nuance. And so that's where like the shell sort and the quick sort would be on the same scale, but the exact implementation, one might be faster or slower depending. So, the quick sort, we've talked about a little bit in the video before. We'll talk about a little bit in an upcoming video. The quick sort is less than optimal because when the data is already sorted, when it's not, when you're not finding good pivots, essentially. And so that's why we shuffle it. And that shuffling adds in a order n, and in my case, an n over 2 slowdown compared to what the shell sort was doing. But you take that slowdown away, again, it's just an order n, then they start behaving about the same. But we'll talk about that as we come back to it. I don't want to get too far ahead. But the big O notation, excuse me, um, typically has a scale kind of like what we saw before. So an order 1 is it's a constant value. It might not truly be 1, it could be 7, it could be 50. It's a constant number of statements across all of them. So, if I say it could be 50, it's not saying that the list size is 50. It says whether the list size is 5 or 500 or 5,000, there's 50 statements. But we don't typically care about what that exact number is. We're just saying the order is constant. As opposed to order n, which could be I do the whole list, or it could be n over 2, I could do half the list. But still a constant order based off the list size. And order n squared is some of the slower problems we talked about. The bubble sort, the insertion sort are around order n squared. Notice from the chart before, it's not to say they all perform the same. Clearly, the bubble sort is the weakest of them. The bubble sort has no cutting whatsoever, but all of the order n squared algorithms are slower than the order n log n algorithms. That's what we're looking at mostly, and we're mostly targeting for quick growing problems like this. Is those fast sorting algorithms are on the order of n log n, and so this is the stuff you'll see, but how do computer scientists come up with this? How do they come up with these answers? How do they get to this resolution? And that's what we're going to look at here for the rest of this videos. So here's an example of looking at the big O notation. This is a really bad, slow bubble sort. Not that it's badly written or anything like that, just not fast compared to everything else. So we start off in here looking at each list item in turn. So it's an order n. So I'm going to print out the list, order n. If I'm going to find an item on the list, it's order n. But we're not doing that, we're sorting. So what we do then is we loop through potentially every other item on the list. I'm sorry, this might be the insertion sort. It's not pull sort, it's insertion sort. Now that I look at it. And so the going through each item on the list again, it might not hit every one. It might just hit some of them, but it has a potential of doing a whole lot of them, depending on how it's organized. And so, again, this is better than bubble sort. It's not truly going through every item. It is cutting it short, but it's still on the order of n squared because in certain scenarios, worst case scenarios, it comes up to being n squared or close to there. It's actually n squared over 2, but close enough. We kind of round those factors off. So there's actually 3 notations that you should be aware of. The big O is the worst case scenario. The omega is the best case scenario, and the theta is when the worst case and the best case are the same. So if you see an algorithm that's theta n squared, it means it can never do better than n squared. Or if you see one that's theta n log n, it's always worst case and best case always look the same. There's no optimal case or suboptimal case inside of those. So the trick to doing this analysis is we have to analyze through all of the different cases and see where things fly. So if we look through this algorithm when the value is already sorted, it actually, if we look pragmatically in this one, in real numbers, it's actually doing 4 comparisons and 0 swaps. So we can look at each of the big expensive operations going inside of here. So it calls less a total of 4 times, and it calls swap no times because the thing's already sorted. So if you consider the algorithm, it starts at 1, so it's actually a little bit less than n. It's n minus 1. But again, we don't care about those details. It's just, the order is going to be ignoring the pluses and minuses and the divides inside of there. But it looks at this, and B and A are already sorted. It's already less than, so it goes to the next one. And then C and B are already sorted. So, hey, good, we'll keep going. And then D and E is already sorted. Okay, well, great. And then E and D is already sorted. Okay, we're done. So the best case scenario, this actually runs as essentially order n. It's not actually there, but we'll come back to that in a second. So here is a jumbled example. And so this is, a situation where we have somewhere in between. It should be a quote unquote normal case. And so if we compare this, well, A and E are actually already sorted. So we keep going. C and E, well, we swap there. We do one comparison here, second comparison, and one swap. So now we have 2 comparisons, 1 swap. And and then we do another comparison here, C and A. Well, those are already good, so we don't do a swap. So now we're at 1, 2, 3 comparisons, 1 swap. Then we come over here, B and E. There's a comparison to swap, and B and C, a comparison to swap. B and A is good, and then so if we continue through this logic, basically we see there's 8 comparisons, 4 swaps. So it's not too bad. I mean, it kind of feels like we're still order n-ish, but it's not bad. So we have 5 values, 4 swaps. That's not so bad. 5 values, 8 comparisons. We're still less than double what the size is. But then we have kind of the worst case scenario, which is we have to swap every single one of them. They're all in the wrong spot. We have to completely flip the array here, the orders the array, and that one turns into 10 comparisons and 10 swaps. So it's a lot of swapping. The comparison seems to be about the same, but this, again, it lies a little bit. It's the idea of small numbers. The feel is you want to look at this and do this by hand, and then empirically you can say, oh, well, there you go. It's, it looks like it's order 2 and 2 times n, right? That's not so bad. But if you actually look at this and you kick it up, if I kick up the numbers big time, do 500 values, well, in the ordered list it'd be 500 comparisons. So it's actually order n. It sticks at order n for the number of comparisons. But for the nominal case, it ends up being around 60,000 at 500. At 500, 60,000 comparison swaps. So if you think about that, 500 squared is 250,000. So it's actually n squared over 2 is that nominal case. I'm sorry, n squared over 4. And then 250,000, for 500 at n squared is n squared over 2 is the worst case scenario case. So the insertion sort, again, if we simplify the math, is n squared over 2, but we can ignore that over 2. So we just say it's order n squared. So yes, over 2 is a big deal. Certainly doing half the work is a big deal, but as far as comparing it with a logarithmic algorithm, it doesn't make any difference at all. I would rather do an n squared over 2 algorithm than an n squared algorithm, but if I can find something even faster, that's all the better as well. So that is a simple case of order analysis. Not all cases are that simple. And so we're going to look at another couple examples here, one recursive and another one we're not even going to bother to tackle, that show us how this analysis can be very complicated but also very powerful at the same time.